All right, so in this lesson, we're basically going to just learn how to graph a logarithmic function, okay? It's really not a terrible process once you know kind of the strategy behind it, all right? So to help us, what we have to recall is that exponential functions and logarithmic functions are inverses of each other, okay? If they're inverses of each other, that means their domains and their ranges switch. And that also means that their graphs are symmetric over the line y equals x. So we've got a graph here of, in blue, this exponential function y equals 2 to the power of x. That's something we've already worked with in the past. It's got a horizontal asymptote, okay? The domain of that is all real numbers. And the range is 0 to infinity. Okay? Now, if we reflect that over y equals x, we get the inverse, which is this logarithmic, y equals log base 2 of x. Its domain would be all reals. I'm sorry, 0 to infinity. And its range would be all reals. So notice how these have just, switched, domain and range, okay? Now, let's just verify that those two are, in fact, inverses of each other. If I want the inverse of something, I switch x and y, right? So y equals 2 to the power of x changes to x equals 2 to the power of y. And I want to solve what's in red back for y, right? Well, this is where logarithmic form comes into play. This is log base 2 of x equals y, right? So that just verifies that, yes, in fact, y equals log base 2 of x is the inverse of y equals 2 to the power of x, okay? Now, one thing we should be noticing from the red curve there, and then its domain of 0 to infinity, we now have a vertical asymptote on the graph of a logarithmic function. All log functions will have a vertical asymptote, whereas the exponentials had a horizontal. Okay? All right, so go to example 1. We want to graph f equals log base 3 of x, okay? So the first thing we'll do is recognize the argument of the logarithm is x. That means the domain has to be x is greater than 0, or you can say 0 to infinity again. That's nothing new. We've said all along, you cannot take the logarithm of a negative value, right? Okay, now what that tells me is the vertical asymptote should be at x equals 0 then. Let's draw that in. Put it in as a dashed line. Okay. Now, the one thing that's challenging, I think, for students when we go to graph these is choosing good values of x to be able to plug into the function, okay? So what's in red here is the key. You want to focus on the base of the logarithm, which in this case is a 3, okay? For the log to evaluate nicely with integer values, we need to choose values of x that are perfect powers of 3, okay? So the first one I'm going to choose is 1. 1 is a perfect power of any base. Okay? If I plug a 1 in here, what is log base 3 of 1 equal? 3 to what power is 1? 0. Okay, so that leads us to our first point at 1, 0. Okay? Now, the next best perfect power of 3 would be 3 itself. what would log base 3 of 3 equal? 1, because 3 to the first power is 3, right? So that plots to the point 31. After 3, I would choose 9 next. What's log base 3 of 9?
3.
Not quite. 2. 3 squared is 9, right? We're working with powers. So we plot 9, 2. All right, what would be the next best value of 9 if I continue to increase? 27. Of course, I'm not going to plug that in because that's going to go off the grid that we've been provided, right? Now, what I'll do is I'll actually go in the other direction, and I will plug 1/3 in. Log base 3 of 1/3. 3 to what power is 1/3? -1. So this point we'll have to just estimate its location. 1/3 -1 is right about there. See how we're getting close to the asymptote now. And could also use 1/9. Log base 3 of 1/9 would be -2. 3 to the -2nd power is 1/9. So again, that's just, those last 2 points are to show you the behavior near the asymptote. Okay? So your curve should be drawn looking something like this. We're getting infinitely close to that asymptote. All right, so again, the key here, in the words of the famous Meghan Trainor, it's all about that base. It's all about that base.
No problem.
Okay? All right, example 2. This one's a little more sophisticated. F of x equals 2 times log base 2 of x minus 3. So the argument of the logarithm has been changed to not just x, but now x minus 3. So I need to take that, make it greater than 0. That's going to solve to x is greater than 3. I'm only allowed to plug in values for x that are larger than 3 is what that's saying. That moves the vertical asymptote to x equals 3. We're getting a horizontal shift here then. Draw that asymptote in. All right, now you'll notice the table that I have set up, I've made 3 columns this time, okay? The first column represents the argument of the logarithm, x minus 3, okay? I need that argument to turn into a perfect power of the base 2, okay? So that first column is where I put my perfect powers of 2. So I'm going to do 1, 2, 4, 8. You could do 16 after that. That's a little too big. And if we go in the other direction, we could do maybe 1/2. Now, those are not the values that I'm actually plugging in for x, though. That's what I want x minus 3 to turn into. So I have to ask myself, for x minus 3 to become 1, what would x need to equal? What number minus 3 gives you 1? 4. That's the actual number that I'm plugging in for x, is 4, which is consistent with the domain. Okay? So 4 minus 3 is 1. What's log base 2 of 1? 2 to what power is 1? 0. Then multiply it by the 2 that's out in front, still 0. So we're plotting the point 4, 0. Okay? Next, I want x minus 3 to turn into 2. So what should x equal to make that happen? What number minus 3 is 2? 5. 5 minus 3 is 2. Log base 2 of 2, 1, because 2 to the first is 2. And then that 1 times 2 is 2. I have the point 5, 2. What should x be so that x minus 3 results in a 4? 7. 7 minus 3 is 4. What's log base 2 of 4? 2. 2 squared gives me 4. So then 2 times that 2 is 4. 7, 4. Next, x is going to need to be 11. 11 minus 3 is 8. Log base 2 of 8 is 3. 3 times 2, 6. That one you have to go off the grid a little bit, but you can still fit it. What number minus 3 is 1/2?
That is
Somebody said it.
1.5.
Yeah. Is that 3.5 or 3.5?
Oh yeah.
So 3.5 minus 3 is 1/2. What's log base 2 of 1/2? 2 to the negative first is 1/2, right? Take that negative 1, multiply it by the 2 out in front, you get a negative 2. Plots right there. So see how we're getting closer to the asymptote on that end. Here's the curve. Any questions on that example? All right, one more just for more exposure. In this one, we are back to the base of the logarithm being a 3. Okay? Start by focusing on the argument, though, of the log. It's x plus 2. For the domain, that's going to have to end up being greater than 0. That'll solve to x is greater than negative 2, moving the vertical asymptote to x equals negative 2. All right, so now that the base is back to being a 3, I need perfect powers of 3. I'm going to use 1, 3, 9, and how about a 1/3? I want x plus 2 to turn into 1. What should x be then? Negative 1. Okay, negative 1 plus 2 is 1. Log base 3 of 1 would be 0. 0 plus the 1 out in front would be 1. So we're plotting negative 1, 1. What should x be so that x plus 2 is 3? Positive 1. So 1 plus 2 is 3. Log base 3 of 3 would be 1. 1 plus the 1 out in front would be 2. 1, 2. Oops, that's 0, 2. What number plus 2 is 9? 7. So that'll give me log base 3 of 9, which is 2. 2 plus 1 gives me 3. So 7, 3. All right, let's show some work for the last one here. What number plus 2 results in 1/3? Well, solve that equation by subtracting 2 over. You would need a common denominator. 1/3 minus 2 would be the same as 1/3 minus 6/3. which would give you -5/3. That's what we should plug in for x here. So -5/3 plus 2 is 1/3. Log base 3 of 1/3 would be -1. -1 plus 1 gives me 0. Plot that, just estimate where -5/3 is. Obviously, we're close to the asymptote there. Plenty of points to sketch out a reasonable curve here.